Hello, my name is William, and today I'm going to talk about my research involving worm castings, Martian soil, and potatoes. I'd like to begin by sharing a quote from Konstantin Tsiolkovsky. "The earth is the cradle of humanity, but humanity cannot stay in that cradle forever." Tsiolkovsky was a Soviet rocket scientist who contributed greatly to scientific advancements while aeronautics was in its infancy stage. The central concept he's alluding to here is the innate desire for humans to explore. Curiosity has pushed humans to develop and advance new and existing technologies, many of which are facets of everyday life. Mankind diffusing the new planets to call home is inevitable, and humans haven't been on the red planet yet. However, space organizations around the world are currently developing housing and facilities to be used there. While it seems far off, firms are harnessing their curiosity to prepare for this reality. It was such curiosity that influenced the development of my own research question. While I was generating my research question earlier this year, I narrowed down my points of interest to a few niche topics. Those that interested me most concerned biology, space exploration, and botany. These subjects became keywords while I was searching for scholarly articles. Some of the articles that stuck out most to me confronted the subject of Mars. My knowledge of Mars previous to my research was minimal. I mainly learned about the red planet via video games and media, but as I explored articles, I noticed many outlined methods of sustainable living on Mars. Perusing the articles further, I found that the subject of living on Mars contained bits and pieces of my three original interests: biology, space exploration, and botany. So I've delved into all things related to humans on Mars. The more I explored, the more my interest solidified. My curiosity guided me to think critically about how to live most efficiently 140 million miles from Earth. I found resources across the internet deriving ways that we can effectively and efficiently produce food on Mars. This subject piqued my interest, and from there I assembled my question. How effectively can worm casting supplement agriculture on Mars? Mars is vastly different from Earth, with complex physical and chemical properties, many of which pose complicated challenges to space organizations. So Mars is the fourth planet from the Sun. The list of differences between Earth and Mars is a long one, but space agencies are mainly concerned with a few key differences. These key issues are temperature, gravity, regolith composition, and atmosphere. Figures from NASA illustrate these discrepancies. Figure 1 here tells how the soil composition of Earth differs from that on Mars. Average soil composition here on Earth is about 50% water and 50% organic and mineral matter. While Martian soil, which is called regolith, is essentially almost all completely mineral matter, with the exception of being about 2% water. Lack of organic matter and water would inhibit plant growth, a primary concern I sought to alleviate. Figure 2 shows how, unlike Earth's atmosphere, Mars' atmosphere is 96% carbon dioxide and over 100 times less dense than Earth's. The lack of gases in the atmosphere would be a threat to agriculture, as well as the fact that the temperature is, on average, over 130 degrees cooler. These disparities pose a major prospective issue for space agencies planning to practice agriculture. Now it came time to devise my experiment. This included reviewing surrounding literature, collecting materials for my experiment, and finalizing my methodology. Before I could undergo an experiment, I needed to make sure my understanding of Mars' physical properties were fully understood. Thankfully, many are curious about this subject, and there is no shortage of information available that would leave gaps in my experiment. Also, NASA has a vast amount of information and literature specific to Mars in the public domain. Specifically, I utilized data collected from the Sojourner, Spirit, Opportunity, Curiosity, and Perseverance rovers. These rovers have wandered around various areas of Mars since the late 1990s, collecting data that expanded our understanding of the planet. If I wanted to accurately conduct an experiment simulating agriculture on Mars, I needed an accurate regolith or some sort of similar substitute. Luckily, a company operating out of Austin, Texas, called the Martian Garden, has created a Mars simulant regolith based off of NASA and their Jet Propulsion Laboratory research. The Martian Garden has sourced basalt from the Mojave Desert and grinded down the rocks to various grades. I chose to utilize soil of the fine grade as it best resembled the general regolith found on Mars. As this figure shows, the simulant contains majority minerals like silica, iron oxide, and aluminum oxide. And because those were all accounted for in the simulant, I chose to utilize around 2 kilograms. Next, I sought after a fertilizer that would supplement nutrients and minerals not present in Martian soil. In my search for this, I discovered Harris brand worm castings. I wanted to use worm castings because the process of vermicomposting uses worms and their biological processes to produce a very effective fertilizer. I also found that figured that a vermicompost unit would be an effective, low-input unit that could be sent alongside a manned mission. This product suited my experiment because it offered a variety of minerals necessary to sustain plant life, such as nitrates and phosphorus, as well as nutrients that come from vermicomposting like iron, sulfur, and calcium. Also, the volume of the worm castings would increase pore sizes, improving drainage and the spread of water. And finally, store-brand petite red potatoes would be used in the experiment. The design of this research project was an experiment to evaluate how well a starchy vegetable could hypothetically grow and reproduce in a simulated environment of a pressurized growing area on Mars. Over the course of about 90 days, a variety of potato was grown and monitored. 2 planting cups were filled with 1 kilogram each of MMS1 Mojave Mars simulant. 1 cup contained only Mars simulant soil called seedling A. 1 cup contained the same amount of soil but blended alongside worm castings called seedling B. Seedlings were to be watered with deionized water 3 times per week. Deionized water was chosen because this water would be filtered and there would be no bacteria that could contaminate the soil in the seedlings and invalidate the yielded results. Seeds received 100 milligrams to 150 milligrams of water on Monday, Wednesday, and Friday from November 30th, 2022 to February 27th, 2023. The environment the seedlings were in was fairly dry, so in the early weeks of the experiment, the seedling planter cups were covered. To avoid research biases, each container was given equal amounts of water. Potatoes used in the seedlings were of comparable sizes, and there's a kind of performance bias that is uneven treatment in study groups. This was mitigated by carefully procuring equal amounts of water on each watering day. Moving on to the results of my experiment. I initially hypothesized that the surplus of nutrients and minerals in the fertilizer would cause seedling B to grow greater in height and volume. Pictured left is seedling B, the fertilized potato plant after about a month. The picture on the right is also seedling B near the end of the experiment. At the end of the experiment, seedling B showed signs of decline. Some of the leaflets of the plant began faltering, as you can see in the pictures on the right. This may suggest that harvesting at 90 days or above 90 days would mean waiting too long. These results are more or less the opposite of seedling A's results. This is a picture of seedling A on January 5th, 2023. This would unfortunately be the greatest extent that seedling A would grow. You can see how tall seedling B is compared to seedling A. Seedling A began to wither at this point despite receiving the same amount of water for the entire duration of the experiment. Here's a picture of seedling A a few weeks before the end of the experiment. Here are photos of the actual potatoes yielded from seedling B. The 2 largest were about 1.5 centimeters as seen on the top right and 2 centimeters as seen on the bottom right. Pictured left is the root system developed by seedling B. Now for the analysis and conclusions. The findings produced by the experiment were interpreted in accordance with the initial research hypothesis. Visual examination of the seedlings shows striking contrasts between the 2 variables. Both seedlings broke the soil on the week of December 12, 2022. However, only the fertilized seedlings survived the duration of the experiment. And even then, the seedlings showed signs of declining health. However, both seedlings, fertilized and unfertilized, planted about 2 inches deep, took 12 days to sprout from the surface. In the following days, seedling B developed substantially more than seedling A. As shown earlier, seedling A eventually died while seedling B produced new potatoes. One of the main limitations of my experiment was that I only created 1 group of trials, seedlings A and B. Creating many more seedling trials might produce dissimilar results compared to the results I procured with my experiment. The hypothesis was that crops planted in soil supplemented with worm castings would produce larger vegetables and grow significantly quicker than those planted in only unfertilized regolith. The hypothesis was supported by visual evidence procured during the duration of the experiment. A manned mission to Mars is expected to take place in the late 2030s. While nutrition is a facet likely to be overlooked when compared to the engineering challenges space organizations face, figuring ways to efficiently grow food would minimize the costs associated with long-distance space travel. The intention of my experiment was to derive one such way to make growing vegetables on Mars effective and viable when supplemented with an amount of worm castings. I would consider my experiment a success in that regard. My hope is that maybe one day organizations pioneering space travel will utilize similar methods to my own to provide food for their astronauts. This was my presentation on worm castings, Martian soil, and potatoes. And here are my references. Thank you.
Couple of questions. How did you determine which results generated by your research method are most important in informing your new understanding?
So I had to look at the garden methods that are mastered on Earth in combination with data from Mars to figure out what issues I needed to focus on.
Okay. How does your new understanding address a gap in the scholarly conversation?
So I outlined a method that showed Martian soil is not only capable of being fertilized for practicing agriculture, but it can actually be done.
Okay. What was the most important research skill you developed as a result of the process, and how could you apply it to your future endeavors?
So being so focused on results distracts you from fully understanding the process of your experiment. So I would say that I learned a great deal about patience in my experiment.
Okay, thank you.